Hello friends, this video on chemical bonding part 27 is brought to you by examfear.com. No more fear from exam. Before watching the video, please make sure you have watched part 1 to part 26. Let's start with the molecular orbital theory. The last theory. The question is, why do we need to study this theory? We already have so many theories. We have learned the Lewis theory, we have learned the Vesper theory, we have learned the valence bond theory. Right? So many theories we have learned. Why do we need molecular orbital theory? See, if you see the oxygen, if you take this oxygen in the lab and experimentally you see oxygen is paramagnetic. This is a liquid oxygen and it gets attracted towards magnet. So oxygen is paramagnetic. Experimentally, this is true. But with the existing model, we could not explain why it is paramagnetic. And also if you see H2 exists but He2 doesn't exist. We don't have answers for all these. We don't have answers for the chemical properties of the molecules. For these we need molecular orbital theory. So to answer these questions, we'll study molecular orbital theory. This theory was developed in 1932. And the features of this theory are, it says that electrons in the molecules are present in various molecular orbitals. See, the whole perspective is different in this case. The other theory talks about atoms and the overlap. This theory says that if I have a molecule, I'll view molecule as one piece. The way we have orbitals in atoms, we have orbitals in molecules. So in this case, the way molecular orbital theory works is it considers molecule as one entity, right? And all the rules, most of the rules which we have for atoms, the similar kind of rules applies here for molecules. Please note. So instead of viewing molecules as two different atoms, it views molecules as molecules itself. And the molecules, see the way atoms has orbitals, right? Atom has orbitals and all these orbitals have different energy, right? And then we fill electrons in this orbitals based on the energy. Similarly, molecular orbital things theory talks about a concept where it views molecules as molecules, and then molecules will have orbitals, and orbitals in this molecule, as molecular orbitals, will have different energies, and when you fill electrons in these molecular orbitals, it will be based on the similar principle, above principles, and those kind of things, right? So the shift here is, instead of considering molecules as two different atoms, it considers molecules as molecules, right? So if you see, it says that the electrons in the molecules are present in various molecular orbitals, because I'm talking about molecule as one entity and I have orbitals in the molecules, that is called molecular orbitals, and electrons are present in that, right? So atomic orbitals of comparable energies and symmetry combine to form molecular orbitals. So how you get molecular orbitals? When atomic orbitals of comparable energies and symmetry, they combine to form molecular orbitals. So the way they have done here is, so this is my s orbital, s atomic orbital. These are my two s atomic orbitals. These are my atomic orbitals. It forms molecular orbital. So this is also my molecular. The one on the, okay, right here. It's also molecular orbital. This is atomic. So in this case, if you see two s atomic orbitals combine to form two molecular orbitals. Here also the law of conservation of orbital will hold true. If two atomic orbitals are combining, it will form two molecular orbitals. One is bonding, this guy is bonding, and the other will be anti-bonding, right? Here also says it is a head-on collision, head-on overlap. It is a sigma s orbital, sigma s. This is a sigma s star anti-bonding orbital. Similarly, you have here also for p also you have head-on bonding, right? This is atomic orbital. It forms one bonding and one anti-bonding orbital. Anti-bonding molecular orbital. Correct. So it is saying that atomic orbitals of comparable energy form a comparable energy and symmetry forms molecular orbital, and then once you have molecular orbital, you try to fill electrons in that molecular orbitals as if you are filling electrons in a atom. I'll explain those things. We will take two examples. Just understand that it talks about molecular orbitals. It views the orbitals in the molecule as molecular orbital itself, right? And says that we have one bonding molecular orbital and anti-bonding. So bonding has higher energy, anti-bonding has lower energy. Sorry, bonding has lower energy, stable. Anti-bonding has higher energy and is pretty unstable. And if you see the distribution also, there is a nodal plane here. Actually, there is a node here where there is no electron. This is also node. There is no electrons here. Here also it is node here. So we'll explain these more when we discuss this in detail. Also note that this atomic orbital is monocentric. If you see, this guy has one electrons, but when you talk about molecular orbital, it's polycentric. In this case, there are two electrons. You see, sorry, two nucleus. So in atomic orbitals, there are one nucleus, monocentric. But if you see, talk about this atomic orbital, molecular orbital, they are polycentric. In this case, two nucleus. Here also, it is something on top of this. So the nucleus is more. If you see this case, there are two atoms. When they combine, there can be SS overlap, right? So when there is SS overlap, it will form anti-bonding and bonding S orbital. See, two atoms combine, that is a fact, experimental fact. Now, the structure, the behavior, all this thing has to be explained. To explain this, there are so many theories. This is a different theory altogether. Don't get confused with the last theory which we have learned, valence bond theory. This is a total different theory altogether which talks about molecular orbital. And don't mix things, because there are different approaches to explain the natural phenomena of chemical bonding. So this approach is totally different from the valence bond approach. This approach says that there are two, see, atom looks like this. That is pretty clear. Experimentally, they have seen this. Now, when atom combines, so valence bond theory talks about orbital overlap, but molecular orbital doesn't talk about all those things. It says that S and S orbital, atomic orbital, will combine to form molecular orbital. Then you have P and P atomic orbital will combine to form molecular orbital. Similarly, atomic orbital combine to form molecular orbital. And atomic orbital is monocentric and molecular orbital is polycentric. Correct? So let's understand this molecular orbital theory in detail. As I told, the law of conservation of orbital is followed here also. The number of molecular orbital form is equal to the number of combining atomic orbital. For example, if you see, these are two atomic orbital, right? Two atomic orbitals are combining, so it gives one bonding molecular orbital and one anti-bonding molecular orbital. Correct? These are all atomic orbitals. So 1s, 2 atomic orbital combined, and it gave 2. Right? It gave 2 actually. You can think of this way actually. Sorry. This is plus, this was minus. And why it is like this? Because these orbitals, as we have learned, are nothing but Schrödinger equation, a waveform. Correct? So we'll explain why it is in the next slide. Just understand that in this case the law of conservation of orbital is formed when two atomic orbital combine, two molecular orbital are formed. One is known as bonding, the other is called anti-bonding. Correct? The bonding will have lower energy and they are stable. The anti-bonding will have higher energy, so are unstable. In this case also, if you see, this is p orbital, this is p orbital. So this combines, they form sigma p, sigma p and sigma p star. This is anti-bonding molecular orbital, and this is bonding molecular orbital. Here also if you see p and p combined to form pi molecular orbital. So this guy is my bonding molecular orbital, and this is my anti-bonding. Right? And these guys have nodes here. This is my nodes. This is my nodal plane, nodes where there is no electron. Here also is the nodes actually. Now the question is why it forms bonding and anti-bonding molecular orbital. So why 2? So the answer is pretty simple. See, this orbital is nothing but my wave function. Right? Atomic orbital is nothing but my wave function. So when I am saying my wave function 1 and I am saying wave function 2, I can either plus it or I can minus it, because there is destructive and constructive interference. Correct? So one output will be you add these two wave function, and the other will be you subtract this two wave function, right? So if this is my wave function, if you subtract this, you get anti-bonding. This subtraction. When you add these, you get bonding. Hope you understand this. See, atomic orbital is nothing but my wave function, right? So, and this can be obtained by the solution from Schrodinger equation. So it can either add or subtract. So when you add the waves, it becomes something like this. When you do a subtraction, it becomes something like this. Here also, if you see, when you add these two, actually, it becomes something like this on addition. On subtraction, it will be something like this. You just subtraction, you flip this. See, for addition, you just add it. So this will become bigger, it will become like this. Subtraction, you flip this and then add. So if you see, it becomes something like this. Similarly, here also, for addition, it will be something like this, it will be added. Subtraction, it will be something like this. This dark and light color is just so that it got flipped. For subtracting, this is plus, this is minus. Subtracting, you have to flip it and then add, right? So if you flip it and add, it becomes something like this with the node here. Here also there is a node. Here also there is a node in case of antibonding. Antibonding has higher energy and they are unstable, and these are bonding. This is also bonding, molecular orbital, bonding MO, and this is anti-bonding M, right? Correct? So this is bonding and this is anti-bonding M. This is how it looks like actually. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.